We have a reliable understanding of how thermal energy works. When you add heat to a solid object, you expect a reaction. The standard rule of thermodynamics is straightforward. Continuous heat input results in a predictable rise in a substance's temperature. Imagine setting up an experiment to track the internal temperature of a block of ice. It starts at -10 degrees Celsius, and you place it over a constant, steady source of heat. As long as the matter remains in a single solid state, the internal temperature climbs in direct proportion to the heat you are adding. It perfectly matches our everyday logic. But an anomaly occurs the moment the internal temperature reaches exactly 0 degrees Celsius. The temperature stops rising entirely. The contradiction? The energy input hasn't stopped. Massive amounts of thermal energy are still entering the system, yet the graph shows a stubborn horizontal flatline. The substance now exists as a mixture of solid ice and liquid water coexisting in thermal equilibrium. Thermal equilibrium is a state where different phases of a substance stay at the same temperature without transferring net heat between them. During a phase change, temperature remains constant despite a continuous flow of heat. If this added energy isn't registering on the thermometer, we have to find where it is stored. The incoming thermal energy is being diverted. Instead of increasing the kinetic energy of the molecules, which would raise the temperature, it is being used entirely to break molecular bonds and change the physical state of the matter. Physicists have a formal term for this absorbed energy: latent heat. The word latent means hidden. For the specific solid-to-liquid transition phase we just witnessed, the energy required is called the latent heat of fusion. We calculate this energy requirement using a precise thermodynamic formula: Q equals m times L. Q is the total heat required, m is the mass of the substance, and L is the specific latent heat constant. That L is not a universal number. It is a characteristic constant that changes drastically depending on the exact molecular makeup of the material being altered. Latent heat operates as a strict, unavoidable energetic toll. A substance must pay this toll in full before it can cross the border from one state of matter to another. This grand, higher plateau represents the transition from liquid to gas. During this phase change, liquid water and water vapor exist simultaneously in thermal equilibrium. The specific term for the energy required to make this second transition is the latent heat of vaporization. Looking at the rates a mechanical reality, converting a liquid into a gas requires a significantly larger deposit of heat than simply melting a solid into a liquid. Every element and compound in the universe undergoes this process, but each possesses its own unique latent heat signatures and phase change temperatures. This table water. Its latent heat of vaporization is a staggering 22.6 times 10 to the 5th joules per kilogram. Water's boiling point is relatively low and common, but its energetic cost to become a gas is unusually massive compared to its mass. This specific property makes water a uniquely powerful storage vessel for thermal energy. Let's apply this to a real-world hazard scenario. Compare the physical danger of exposure to 100-degree liquid boiling water versus exposure to a jet of 100-degree steam. Medical reality dictates that a burn resulting from steam is radically more destructive to human tissue than a burn from boiling water. This happens despite both substances registering at the exact same temperature of 100 degrees Celsius. The math identifies the source of this extra energy. Steam carries a massive payload of 22.6 times 10 to the 5th joules per kilogram, the latent heat of vaporization. Upon contact with cooler skin, the steam condenses back into water. In that fraction of a second, it instantly unloads all of that stored latent heat directly into the tissue. Temperature only tells half the story of a system's thermal energy. Latent heat is the true measure of a phase's stored power.